All right, so a couple of things before we start. I actually meant to get this at the end of last week. I was sent this. I don't know, have any of you guys participated in any of the economic experiments here? A couple of you. So I put up an announcement. I just copied over an announcement. They sent me this flyer at the end of last week. If you're interested in making a little bit of extra money, these are things you can participate in. I don't know how the ones they're running right now. I don't know exactly how long they are. Usually they're like anywhere from, I don't know, an hour. I don't think they usually go longer than 2 hours. Sometimes they're even shorter than that. It just kind of depends on what the experiment is. Probably help if you can see this. But this has a QR code. You can kind of find some more information about ones you can sign up for. I actually mentioned this somewhat at the beginning of the class, these experiments, but that information is kind of on the announcements tab. So that problem set was due when we met in class today. That was kind of the extended, where is it at? All right, the extended due date going to be today. You have that quiz from last week. So after class today, I'll be fully transparent. I'm hoping to get it posted before I leave today. If not, it'll definitely be posted tomorrow. I've got the next problem set and kind of quiz ready to go. I'm not going to post the quiz because we haven't covered all the material until after Thursday's class, and I just don't want someone to take it and then tell me, I didn't know we hadn't covered everything, so I didn't know how to answer the last question. So that'll be posted after Thursday's class when we've covered all the material. That'll be due at the end of next Friday. So you've got some time to start working on those practice problems. It's primarily going to be what we were talking about already, though, prior to this week, which was interaction terms. So that's going to be the bulk of it. It's just some of the last few questions on that quiz are going to be what we talk about today and tomorrow. That problem set, similar kind of idea, mostly what we did with interaction terms. So once you see that posted, like I said, I'm hoping I can get it together. I'm just dotting my I's, crossing my T's. I want to make sure everything's good to go with it. There's no typos or anything. So I'm kind of reviewing that problem set. You'll either see it pop up later this afternoon or somewhat early tomorrow morning. Okay. So that's kind of where we're at. We're going to start on kind of the next topic, which is not interaction terms, but data issues. I'm hoping that we go through a little bit quicker. Thursday's class, I might actually kind of have some time set aside that maybe I pull open that problem set and maybe give you some guidance. So it might be a really helpful class to be at, since I might be doing some of literally exactly what I'm asking you to do in it. Okay. So other than that, we've got that data issues kind of slides I'll kind of start with. Any questions for me before we jump into material? Shouldn't have a lot of housekeeping stuff to go with us right now. Another thing I wanted to mention. So I can't remember. Did I go over this last week, kind of telling you about that hypothetical grade tool? If not, it's right here. So I put it under the files tab. If you download this, I think I did go over this a little bit after the exam, but just in case I've gotten a question or two about it, you can kind of put in what your current grades are and the problem sets, quizzes, and the midterm, and then in-class quizzes, and you can kind of play around with that final exam grade to figure out what your hypothetical grade in the class would be. So this person would be like, if you had 90 on the problem sets, 80 in the quizzes, all the in-class quiz points, and you got a 76 in the midterm, what would you need to get different grades? You could kind of start to play around with this. If I enable this, there we go. If I get 100, here's my grade. If I get a 50, this might help you out, divert your kind of time. I know you have more than just this class, so if you're thinking about where's your time marginally most effective, this tool will be helpful, at least in determining that for this class. Okay, so that just lives under the files tab on Canvas there. Okay. All right. So come down here, and we will think about data issues, right? So we've actually kind of already talked about some of these things, just not in a direct context. So the first thing that we're going to talk about with issues that can exist in the data. So you've got this data set and you went out and found it, or it's been given to you. We have two types of validity that can be violated, right? So the first, there we go, is going to be internal validity, right? So this is going to be that we're trying to get this cause and effect relationship, and The one internal validity concern we've already talked about is if I don't have variables that matter, what's going to happen to my coefficient? We said it's going to have what kind of bias? So if we don't have variables that matter, we have important omitted variables. So we said our coefficient will have an omitted variable bias, right? We'll get the true effect plus some additional amount, okay? So we'll see that a little bit. I think I got some more examples of that today, but that's one thing we haven't really called it internal validity concern, but that was one we've actually already talked about. Even if we've got accurate data, right? If we estimate this relationship without important variables, our coefficients won't be what they truly are. They won't be the true population coefficient. Okay? Actually, what are some other internal validity things that we've actually already talked to now up to this point? What's another way I might end up with an incorrect coefficient if I'm trying to estimate the cause and effect relationship between two variables? I might have the wrong what? So what if I estimate as a linear model, but in fact it should have been nonlinear? Well, there my coefficient estimate isn't going to tell me the true cause and effect between those two. It's right. I'm trying to fit the wrong relationship. So that would be kind of an internal validity concern as well. Right? Anything that leads us to having a coefficient that isn't going to accurately capture the cause and effect relationship. Okay. Now, the things that we haven't really talked about, or at least directly, are going to be external validity concerns. So external validity concerns usually is going to be if I've got, right, a data set that has a population, or at least it was sampled from a population that doesn't match up with the population I'm interested in. So let's say I want to know kind of how hours studied is impacting student performance. Well, if I'm interested in how it's impacting high school student performance, but my data set is coming from the test performance and hours studied from college students, those are two different populations. So external validity, I'm trying to take the results that I got from one population and extend them to another. Those might not be the same, right? You can imagine that you putting, hours studied might not have the same effect on your test performance as it would for a high school student. Now, more generally, what could this also look like? Well, maybe it's something like if I've only got, let's say, what's a good one? Let's say I go out and gather a bunch of data, right? On, I don't know, I just start surveying random people around campus, and I gather data on drinking habits and their overall level of health. And so maybe my health metric is, I don't know, their current blood pressure. Somehow I'm measuring their blood pressure, and well, if I start walking around campus and doing this, who's the population I'm primarily going to end up with in my data set? Mostly college students. So what do you think is going to end up happening with the data I have on drinking behaviors? If I try to, do you think it's higher or lower than the average population? Higher. So I'm going to have a population where I'm gathering data that isn't going to match up with, if I want to start to make statements about the general population, I now have a data set that is going to have an inflated or have a higher values for that variable than for the general population. Not only that, my guess is drinking more is not great for your health, right? It's not great for your blood pressure, but all of you are relatively young. It's probably not going to impact your blood pressure as much as if someone's drinking the same amount you are and they're 65, right? So if I've got a population, I have to be really careful. It might seem stupid, but it's not. It's usually just a little bit not as obvious that I might have certain populations that are oversampled in my sample. And right, if I want to make statements then using those results and extend it to the general population, I need to make sure my sample looks like that general population. Okay, so that's the idea of kind of external validity. Can I take my results and extend them to making more generalized statements? Okay. Now, when is it not violated? So a lot of times this is like just decision making. So this is why those economic experiments, they don't necessarily care that primarily if they're running these, what are most of the people in those economic experiments? College students, right? Why don't they care? Because they're not trying to estimate the relationship between things like drinking habits and blood pressure. They're looking more at like generalized decision making. When you're presented with certain costs and you're presented with certain incentives, what decision do you make? Or if you're, gambling, right? How do you gamble, in this little kind of economic experiment relative to the pop? So they're not as concerned because those results should be a little more generalizable. It's a hard word to say. Generalizable, right? Or they're not really as worried about that external validity kind of, being invalid. Okay. So this just kind of setting us up thinking about these things. This one I won't really spend a whole lot on. So it could be differences in our populations. It could just be differences on settings, right? So here's the example I always use with this. Even if it was, I had the same population, I make sure I've got the same population. So maybe I'm just really worried about student voting habits, right? Or kind of how students are impacted. I guess you already did ad campaigns, maybe not voting, but ad campaigns. If I run alcohol ad campaigns on IU's campus, and I want to know how is that marketing going to impact the increase in sales? That might be very different than if I run those same exact ads at BYU. If you're not aware, BYU is like a very religious school, right? And technically, if you're Mormon, you're not supposed to drink. So those ads might have almost no effect, right? So it's not just that the population in terms of age and these other characteristics matter. Sometimes it's just the setting that you're in. And in fact, we can sometimes be worried about this in the economic experiments. So I'll use the example of if I had an economic experiment where I'm looking at the gambling decisions of individuals. They've run these economic experiments where they look at like, what payoff do you need in order to accept a certain amount of risk? Well, what's the problem? If you're at a casino and you're actually gambling your hard-earned money, why might running these experiments where I'm giving you artificial money in the lab might not match up with what you do in real life? In the lab, yes, you are going to have this artificial money you're gambling, but are you losing actual money that you've earned? No, right? And so the subjects might view that money, even though it might result in them getting paid a higher or lower amount from these economic experiments, they view it differently than they view actual money in their pocket, right? So settings matter, populations matter when we're thinking about threats to external validity, okay? So I've got kind of a quick and easy example here. Gives me an excuse to pull up Stata here to start out today. So I've got life expectancy data. So I'm going to go ahead. I don't think I have it updated. So we'll go and open it. This is on my OneDrive. I'm going to copy and paste this so I can start using globals. So once again, you don't always have to do this, but because I have to jump back and forth in between computers, my global is going to change. So, right, we can kind of set what that global path is. And then no matter if I go to a computer that's not mine or, whatever, it's going to go to my OneDrive, grab that life expectancy data. So got that life expectancy data opened up. Okay. So I had some different variables in this data set. I had the natural log of BMI, the natural log of GDP. So this is where maybe I've shut down some of the internal threats of validity. Maybe I'm not worried as much about some of these additional controls. If I run this regression where I'm trying to estimate the relationship between BMI, average BMI in a country, and their average GDP. So I'm going to go ahead and run this, and I'll kind of talk about that if statement in a second. Just to kind of get some practice, how would I interpret this coefficient? So I've got a log-log model. So how would I interpret that coefficient? If GDP is measured in, and I think here, if we look at it, I'm guessing it's not quite dollars. So where's our GDP? Oh, nope, looks like it is measured, right, in dollars. So if the GDP goes up by what? $1? No, I took the natural log. So if the GDP goes up by 1%, what's the predicted change in my BMI? It's going to go down by 0.002. 0.002%, right? When I take the natural log, everything of those variables is now in percentages, okay? So if GDP goes up by 1%, my Y variable of BMI predicted to go down by 0.0026%, okay? Now, I have this additional if statement in here, which basically I'm only using the countries in this sample that were considered as developed countries. Right? So this is as income goes up, what's happening to BMI. So if I'm thinking about developed countries, this would be like the US, right? China, India. As people have more money, what are they probably able to do? Buy more. So BMI is a measure basically of how big you are, right? And I'm making this very, non-technical. But if the average income in a country goes up, do you think the average BMI is going to go up or down? They can afford more food, it's going to go up. In fact, we also see they can afford more sedentary lifestyles. You're not out working in the fields as much if you're living in a country that's pretty prosperous, right? But you are more likely to be sitting behind a computer, right? So maybe I see here, okay, actually looks like having more money. Well, actually BMI is going down. So in these developed countries, what might be happening? Well, even though we can afford more food, what might we also be more of? Like we might be more health conscious, right? We actually have the luxury of being able to worry about eating too much, right? So in these developed countries, I found a negative relationship, right? Now, if I instead only had a sample where I only had developing countries, notice what do I find is true about the sign of the coefficient now? Well, now a 1% increase in GDP predicts that the BMI of that country increases by 0.0015. Well, why? What's probably true about the average BMI in developing countries? Average incomes are probably a lot lower, so not as many people can even afford to have a lot of food. So it's probably the average BMIs start out a lot lower in developing countries. So if I give them more money, they're now able to actually be full. They can actually afford more food. So we're going to see they go from maybe being more malnourished to actually a good BMI range. Whereas in the developed countries, the average person in the US has a BMI that is unhealthy. Like, literally, the average BMI in the US is that you are unhealthy, right? And so if we have more money, well, maybe now we can find different ways to try to be healthier and actually reduce that BMI. So it works in exactly opposite directions. We have a completely different sign of our coefficient because our sample contained two different populations. So if I only had one of these samples, let's say I only had my developing countries, and I say, well, look, giving people more money, it's going to increase their BMI. That's a bad thing. Well, I mean, if we look at a developed country, that's actually not the effect. It's actually in a developed country, it's the exact opposite. So we have to be worried about, are we taking results from one population and trying to generalize them and, apply them to a different one? Does that make any sense what I'm getting at here? I don't think it's too crazy. And you could do a kind of the same thing with GDP and population. This one I kind of chose because I wanted to make the point. Sometimes things are more generalizable, right? So here, doesn't matter if I'm in a developed or a developing country. As a country's average income goes up, you're making the decision, or at least have some influence over whether or not you have children. When do you think you're more likely to want to have children? If you have more or less money? More, right? And so here, whether or not we're looking at the developing countries or the developed countries, what is our coefficient? A 1% increase in GDP increases population in that country, right? So 1% increase in GDP increases the population by about 0.8%, right? So here, even if I only had developing countries, that result is a lot more, I can use that and extend that to developed countries. There doesn't seem to be kind of as much of a difference between those two populations. So sometimes, even if we have different populations, the result might still be more generalizable. When it comes to like the BMI, it wasn't. Right? So we've got to be kind of cautious with this, okay? Any questions over that before we keep moving? Okay. Shouldn't be too bad. So that's kind of starting out kind of easy here today. So we've already talked, I already led into this a little bit, but internal validity concerns, we already said it's going to be things like omitted variable bias. Maybe I've got the wrong functional form. I'm estimating a linear instead of a log linear, or I'm not including a quadratic term. So what that's going to do is, A, it might cause our coefficient not to be correct, or it'll cause it to be biased, right? However, it also might mess up our standard errors if we have internal validity. Right? So it doesn't just have to be that we're getting a wrong coefficient estimate. It could be that we're getting the correct coefficient estimate, but the statistical significance is incorrect. Okay? Either one of those would be a threat to internal validity. And think about why. So let's say I ran a regression, and let's say the effect between population and or GDP and population we had was exactly 0.8, right? So I run my regression, I get 0.8. However, I had some kind of internal validity, maybe this was a functional form misspecification, that led to my standard errors being really high. My standard errors are really high. Is it going to be more or less likely I can reject the null? So once again, if it helps, I mean, honestly, I can usually think through this, but it also makes sure I don't make a very easy mistake. What's our test statistic? It's our coefficient estimate over our standard error. So if our standard errors become really high because of something we haven't talked about yet, we'll talk about later on, like data issues that might cause this, what's going to happen to my test statistic? It's going to be much lower, which means what's going to happen to my p-value? Which means it's going to be more or less likely I reject the null. So if I can't reject the null, what did I actually find that coefficient was equal to? Exactly. So even though we find, right, the correct coefficient from our estimate, if our standard errors are impacted by internal validity concerns, we might actually not be able to say it's any different from 0, when in reality, we should have been, right? If we had the correct standard errors, we could have been able to reject the null. So it's not just the estimate we worry about, it's the standard errors as well. And some of the data issues we'll talk about, they impact our standard errors and not just our coefficient estimate. Up to this point, the things that we've talked about, omitted variable bias, functional form misspecification, those really were only impacting our coefficient estimates, right? But we also now have this added thing, data issues that might just impact our standard errors. Okay? All right. So what's one of those things that we actually have kind of talked about? Heteroscedasticity, right? If we have some heteroscedasticity in our errors and we don't account for that, we don't run that robust command, we said our standard errors are going to end up being too high, right? From just not controlling for that. And then it might result in we can't reject the null, in which case, it doesn't matter if we get the correct estimate for beta hat, we can't say it's any different than 0. Okay. So we really, this is what we already talked about all these things, right? We're just kind of rehashing a little bit. But we can do a little bit more work with the omitted variable bias than we kind of did before. So, I'll just put all this out here. So what are some solutions that we have? We have an omitted variable bias, right? So the first thing we can kind of do is we're going to identify the coefficients from the data that we have. We know there's omitted variables that we wish we had data on. We don't. We're simply going to run our regression and look at the coefficient estimate that we see. Okay? So this might be something like have your hours studied. This might look similar to your problem set. And I have your grade, your average GPA. Well, I can look at see what that relationship is. But I know I have an important omitted variable, which is whether or not you also have a part-time job. Well, if I don't have data on that, I know it's going to be correlated with probably whether or not you have a GPA and correlated with your hours studied. You just don't have as much time in a day. Now, if I don't have data on that, I can't include it in my regression, but what I can do is simply run my regression and be aware that my coefficient is going to have this bias. Excuse me. So I've identified now the second part where I think the bias might be coming from, which is this omitted variable of did you have a part-time job? From there, we can think about, okay, is this going to cause my coefficients to be closer or further away from 0? Right? So if I do have the data, what I can actually do is run my regression. So maybe I have 2 different data sets. One of them has whether or not you had a part-time job, one doesn't. I can run the one, maybe it's smaller, that has the part-time job information, kind of see how much is that influencing or what kind of bias is that creating. And then based off of what bias that creates, I can adjust results I get from data sets that don't have that part-time job variable so I can get a more accurate idea. And I'll walk through this with an actual example instead here. I think it'll make a little bit more sense. So one thing that we're going to try to do is we'll start saying is if we can put a sign to the bias. What we ultimately would like a lot of the times is if we can find an attenuation bias, right? So what an attenuation bias does is it helps in that we're never going to see the complete opposite effect, right? if I have an attenuation bias, it could make my result smaller, but it'll never change the sign. So in that case, we're kind of okay with it because we're like, look, we can run this regression. We know we have what we call an attenuation bias. The result is going to be closer to 0. So we know we're going to be understating the effect, but we at least know that we're finding the right sign, right? So we know that we're understating things. So in general, if you're making predictions, you'd always rather I always say, oversell, or sorry, undersell, over deliver. This is the idea here, right? We're going to undersell what that effect might be. The actual effect we know is going to be something larger if we have an attenuation bias. Okay. So some other solutions that we haven't talked about are going to be instrumental variables and some strategy of the panel data. So that's going to be stuff that comes after this week. So we won't touch on this week. We'll dive more into omitted variable bias in the subsequent weeks. And then we're not going to be running any experiments in this, in this class, but that's another way you can kind of shut down some of these omitted variables that you don't have information on. Okay. What do I want to say here? I think we'll can kind of keep moving. Let me see if there's anything I want to do here. Yeah, that's where I want to go. All right, I'll waste a little bit of time here. Nothing too crazy. Oh, there we go. So if I have the wrong functional form, we've kind of already talked about this as well, I might end up with the wrong coefficient, right? So we haven't really talked about probit and logit regressions. If you were kind of can continue taking a class after this, you would start to dive into that. So that's some different regressions you can run when you have these binary 1-0 variables as your dependent variable. We're not going to do anything kind of here, but when it comes to functional forms, thinking about, am I estimating a log-log relationship when in fact it should be log linear? That could also cause some bias in our coefficient estimates. Okay. So we're going to move on to things that we actually can talk about and can control. So let's say I've got data, and here we'll step away from things we have talked about to things that we haven't. So I think that there's a data issue that exists, which is that I might have some errors recorded in my variables. Okay. So if I have alcohol consumption, any time use data you're looking at, if I ask people about their physical or mental health, it's wild. When you look at survey data, so they've done this where they ask people how healthy they feel on a rating of like 1 to 10, and then they actually measure things like their blood pressure. What do you think? On average, people tend to think that they are actually, so it kind of depends on age, right? But if you look at young people and you ask them how healthy they feel, on average, they underreport how healthy they actually are, right? Whereas older people tend to kind of over-report how healthy they actually are, right? So it doesn't matter which way that error is going. I know that when I especially collect things with survey data, people, they don't mean to lie to me all the time. But how do I know what my health is relative to the, I don't know exactly where I would fall on a 10-point scale, or, how much alcohol do I consume a week? Well, I don't know. I'm not sitting here counting drinks. So maybe I tell you 5, but maybe I had 7, right? On that. So it's going to be things that maybe people aren't maliciously lying to you. Now they might be maliciously lying to you, right? Maybe, I start asking people how much they drink on average every week. And I happen to get someone that belongs to an organization on campus, and they're like, oh, I drink so much every week, right? They want to like act like they're this, for whatever reason, they want to report this high value. Well, people might maliciously lie to you as well, right? But it doesn't matter, right? All we care about is that when we collect data, sometimes it's going to have a measurement error involved in it. So we're going to say that X, the variable that we are recording, has measurement error. When we look at the actual data, all we see is what was reported. It includes this measurement error, right? Some people are lying to us. Some people are just incorrectly giving us values they think are right, but they're a little bit off. So we've got X tilde, right? I think I've got this running off the screen here. No. Yeah. There we go. That's what I wanted. So what we're going to actually see are these values for X. The actual values are going to be X tilde. So the difference between those two is going to be what we'll call our measurement error, right? It's the actual X minus the reported X value, okay? So when we're running this regression, right, we could kind of decompose this into being 2 different things. So we're going to have what the effect of this value that we see in the data X tilde is, but then whatever our measurement error is, it would also be kind of picking up part of that. So how can I maybe, how can we think about this in a slightly different way? So let's say I've got beta times X, right? When I look at the actual X values, this is what the effect should be, right? But when I look at my data, all I'm seeing is X tilde, right? So when I'm trying to predict any Y value, I can make the prediction from what I can observe, these X tildes, but how is the actual Y impacted? Well, there would have also been an effect from what wasn't reported, right? So this is what was reported, and I can see that in the data, and I can use that to make predictions for what Y is. However, I know that Y is also going to be impacted by what wasn't reported. So it's almost like this is kind of like an omitted variable, right? So there's going to be an amount that when I go out and collect data that isn't reported to me, it still is going to influence whatever that Y variable is. I just don't have data on it, right? So if I don't have data on it, essentially becomes an omitted variable bias. Where does this actually end up? It ends up in my error term, right? I can't observe that measurement error. It's not a separate variable, not a column in my data set. It just ends up in my error term, okay? So this is what my actual kind of Y value should be. It's influenced by kind of what the self-reported X values, and then also whatever that measurement error is, right? So we would kind of call U here, I think I have a composite error. Do I have it here? Yeah, my composite error term, right? So we can't observe what that measurement error is, so it just gets absorbed into our error term when we run our regression. So when we actually run the regression with the X values that were reported to us, X tilde, our error is going to absorb all of that measurement error effect. Okay? So what might be violated, right? So we'll think about this. So let's say one thing that we said we wanted to be true was that usually we would write, usually we would write that our error terms for different values, we want to make sure that those are equal to 0, right? The expected value of the errors that we're making, right, when we're running this line of best fit, we want kind of the average error we're making to be equal to 0, right? So if I condition on any value for X, the average errors are always 0. We said if I had like a functional form misspecification, that might not be the case. Here, I've drawn one that is the case, right? The problem is I don't have the actual X values. If I run my regression just from the reported X values, well, now I don't just have my error term here, right? My error term absorbed the old error plus the measurement error that now exists, right? The part that is not being reported to me. So now when I run this regression, what do I need for my coefficient to actually be unbiased? Well, I need the expected value of my entire composite error term, U. And now it's not that the expected value needs to be equal to 0 for different values of X. It's for different values of X that are reported to me, right? So I'll go back to my example where let's say, actually, I'll think of a different example where I can guarantee you that this is going to be violated. So if I have a situation where I'm asking people, let me think of a good example here we can use today. So let's say I'm asking people how much money they spent on, I don't know, fast food in the last month. Well, if I have to give you an answer in the next minute or two, I mean, I'm not going through my bank statements. I'm not going through looking, I don't know how much cash I've spent. People will tell me how much they think. So some people are probably going to tell me amount that is too high. Some people are probably going to tell me amount that's a little bit too low. So my measurement error, it doesn't matter if I buy fast food a lot or a little bit. It's likely I could be underreporting or I could be overreporting to you. I'm going to be off by a little bit. I might be close, but I'm going to be off, right? I just can't, from my memory, recollect. So there, for different values of what's reported to me, how much money is being spent on fast food, well, what's going to be likely be true about my measurement error? There's just as many positive as negative values. So the expected value of my error, if it includes the measurement error, well, the measurement error here now is still going to be an average of 0, right? People are just going to be a little bit off and not directionally. Now, let's say, I'll give you another example. Let's say instead I go around campus, I start asking people about how much on average they've been drinking this past week or the past month or something. Well, here's a scenario where let's say I want to estimate how much they're drinking based off of, or sorry, let's say I want to estimate what their age is based off of how much they're drinking. What's going to be a problem? Anyone who's under 21, how much are they going to report to me drinking? Let's say the person doing the survey is a police officer. What might you report to them? Or, yeah, vastly under that, right? So you know that when age is lower, what's the measurement error almost always going to be? You're always going to see people underreporting to this cop. So what your measurement error is always going to be negative. So here, my measurement error is always going to be kind of like in one direction. So I can kind of think about in that case, if people are more likely to lie or misreport in one direction, and if that varies with how old they are. So in my example, if they're under 21, we know that they're likely to underreport. But for different values of X, as soon as they're not 21, what's going to happen? I mean, I don't care if this cop knows how much I'm drinking, right? So there's a different incentive. So there, the values of X would kind of depend on whether, how much I'm lying to you, right? I guess I'm talking this in more general or a little bit technically not correct here, but just to kind of give you an idea that it's really going to be anytime there's measurement error that is dependent on what the actual values for X are, right? So here, if that's violated, right, we have people lying in certain directions given those X values, our kind of conditional error, or sorry, our conditional mean error being equal to 0, that is going to be violated, right? So we don't, we're concerned about that. We're concerned if we have measurement error that violates this, okay? So here I've got it kind of written out slightly differently, right? But here's the actual values we observed. Now my composite error includes some of that measurement error as well, okay? Now, if I estimate this, there's some good news and bad news, right? So if I run this regression with my variable that has measurement error baked into it, the coefficient estimate I see will be the actual coefficient plus this additional term, right? Now I can rewrite this, right? Because if I've got the covariance of the reported X values, and I'm not going to make you rewrite all of this. We just kind of worry about where we get to here. What would the covariance of X tilde with my error term be? Well, if people are lying, depending on what the different values for X are, then that's going to be something other than 0. What should the value of my just more general, not my measurement error, but just the error that's involved? Well, that covariance should be 0. So that one is going to go away, right? So all we're left with is the covariance of this self-reported X value with the measurement error and negative beta 1. Right? So here, I just got that covariance, the covariance of the self-reported X values with just the more generalized error term, that's 0. So that goes away, okay? Now, if I rewrite X tilde, that's what's reported to me. X tilde will be the actual X values plus the measurement error. So when I'm writing error here, just for the sake of space, really this term, the word error here, you can replace with measurement error if that helps you kind of keep these these two separate, right? This was like the error that existed just in my general regression if I had the actual X values. I don't have the actual X values, so the data I observe has this measurement error. Okay. So what's the coefficient estimate I see going to be? Well, I've got beta 1 here. I can kind of pull that out front. Oops, there we go. So if I pull beta 1 out front, what am I left with? Well, the estimate I see is going to be beta 1 times 1 minus the variance of the measurement error divided by the variance of the actual X values plus the variance of the measurement error. Once again, if I rearrange this a little bit, I get that the coefficient estimate I see will be the actual effect times this ratio. Okay, so once again, don't worry, I'm not going to make you like reproduce all of this, and we're never going to have to. This is just support as to why when I have measurement error, as long as I still have that mean conditional on the original error term being equal to 0, that would go away. This would all simplify down to, this is the coefficient estimate I will see. It'll be the true estimate multiplied by this. Right? So I'm going to write this out, and we'll think a little bit harder about what this is telling us. Okay. So I know I'm doing some hand waving. We're not focusing too much on the math there, but it's because I'm not going to make you kind of reproduce that. So if I have measurement error, I'm going to see the estimate for my regression being beta 1 hat is the actual coefficient, what it should have been, times the variance of the actual X values. Okay. Variance of the actual X values divided by the variance. And here I'll write the word out as opposed to the slides just to make it a little more clear. Plus the variance on my measurement error. Okay. So notice, if I have what we call classical measurement error, right? What is, or what is that one? Yeah. So I have my classical measurement error. If I don't have measurement error, what does my estimate go to? So if I have no measurement error in my X value, what would the variance of my measurement error be? 0. So anything divided by itself is, so I actually end up with a coefficient estimate that would be the actual true population estimate. So if I don't have measurement error, we're back to where we have been, right? Kind of where we started. Now, if I do have measurement error, even if it's random, so this is the idea that people can't remember exactly how much money they spent on fast food. Well, the worse people are at remembering how much they spent, the higher that measurement error's variance gets. What's going to happen to the difference between that estimate I see and the actual coefficient? Well, the estimate I see, when this is going up, what's happening to this fraction? The denominator is getting larger, so this would be going, so the estimate I see is actually going to get lower and lower. So as my measurement error variance gets higher, that gap in between my estimate and what it actually should be is going to get larger and larger. And I should be careful here. I put this in this direction. We're just worried about the difference. So the absolute value, right? We just care about what the difference is. We don't care if this one's higher or lower. We just care about how far away it is. Okay. Is that making sense there before we keep moving? Okay. Now, what's another good thing about, well, I shouldn't say good. What's some good with the bad news? If we do have measurement error, what is going to be true about my estimate always relative to the actual estimate? This fraction always has to be less than what? Yeah, if I'm adding in my measurement error variance, the denominator will always be larger. This has to be less than 1. So I'm always going to be seeing an estimate that's a little bit too low. And when I say too low, if this was negative, I'd be seeing a smaller negative value. If this was positive, I'd be seeing a smaller positive value. This is what we would call an attenuation bias, right? This bias is going to cause our estimate to essentially be, right? So if I think about this, closer to 0. right? So this is where we don't care, we care because it's not the right value, but we don't care in the sense that it's going to have the right sign. It's just going to be understating the effect. It's going to be closer to 0. Okay. So you can imagine if I'm running these regressions, if I see an estimate that's going to be a little bit lower, what is it going to be? More or less likely I can reject the null. Well, what's going to happen to my test statistic here? It's going to be smaller, which means my p-value is going to be larger, which means it's going to be less likely I can reject the null. Okay. So we have measurement error in our independent variable, our right-hand side variable x is what we were talking about here. We're going to have what we call attenuation bias, right? So it's going to make it harder for us to find statistically significant effects, and it's going to be, provide us with estimates that are going to be a little bit understated. It's kind of the end of the story there. Okay. Any questions before I keep moving here? Is that making some sense here when we've got? All right. So this is kind of a little bit of summary of what we were just talking about, right? But it's going to cause an attenuation bias, going to push us closer to 0. We've got some solutions, which we won't talk about in this class. They're a little more advanced. We will end up by the end of the semester talking about instrumental variables. So for now, we're just going to say we could just understand that this bias exists. We'll actually talk about a solution to it later on this semester, which is instrumental variables. Okay. Now, everything that we just ran through was kind of assuming that those errors were what we call classical, right? They weren't depending on the actual values for x. If we have non-classical measurement error, so then the covariance of our measurement error with the actual x values, one of the simplification steps that I was using here, I kind of glossed over, was here, the actual covariance of x with our measurement error. We were needing that was equal to 0 so that this covariance kind of went away. Well, if it's not classical and the actual measurement error depends on the values of x, like people are lying to me in a direction that's correlated with what the actual values for x are, it doesn't simplify down to this nice, easy kind of attenuation bias. So if we have non-classical measurement error where the values of x actually do influence that measurement error, kind of all bets are off, right? An example I also sometimes use with non-classical measurement error, if I ask people to kind of self-report what they think their intelligence level is, on average, this isn't true about everyone, but this is just kind of averages, people of lower intelligence tend to give you a measurement error that's actually positive. They over-report, right? Because they don't even know what they don't know, right? I might think that I have some friends from back in the day that they think they understand everything about the world, and they probably, they can look at statistics and tell you exactly what they mean. They have no idea what those statistics are actually telling them, right? They don't even understand that they can't copy. So people of lower intelligence tend to think that they're smarter than they actually are. Whereas people who become more and more intelligent, what do you become aware of? So for example, being in this class, this was kind of like where I started to realize this, but for sure when I got to grad school, I would sit in a class and I'd be like, look, I'm kind of understanding what's going on, but I also understand this isn't even the top level yet, right? I'm starting to realize how much I don't know. So I ended up was in grad school at the time. I'm fairly intelligent, but if you would have asked me, I'd be like, yeah, no, I'm by no means. I know there's these ultra geniuses out there, and I am nowhere near that, right? And so people who have higher intelligence levels, what do they tend to do? Underreport. I can guarantee you a lot of you would tell me if I ask you even your understanding of the material in this class, I don't get it at all. Okay, but if we're just comparing you to the entire population, you are much more aware of what's going on in this class than 80%, 90% of the, even if you think about other people who are in college, I'm going to tell you right now, an anthropology major dropped in I shouldn't pick on anthropology majors, especially since I'm recording it. But if you drop an anthropology major in this class, they're definitely going to be way behind all of you, right? You are going to be much more intelligent than them. Right? I need to be careful what I say. So sometimes I get going and I don't think about what I'm saying. So, so this would be a situation where we don't have classical measurement error because what's reported to me is going to depend on the actual underlying value of X, the actual underlying intelligence level. Okay. Also, my sister was an anthropology major, so I feel like I have like a, I can kind of pick up them a little bit, right? Okay. So let's look at this a little bit in Stata. So I've got this life expectancy data we'll keep running with. I'm going to scale GDP. What did I do? By millions, just so it makes it a little bit easier to look at. So there weren't all these like crazy things. So I'm just going to scale it. We'll then run this regression where I look at BMI and GDP. And I'm going to artificially create some measurement error. So here, this is kind of a cool thing I can do, is I have the actual data, and I can actually create measurement error to kind of prove to you some of the things that we're talking about, right? So the actual BMI values and the actual GDP, I know the true coefficient estimate here because I have every country in the world. I know it should be, what, 60, an increase of 1 in BMI should increase GDP by 60 million. Since actually not 60 million, right? It would be what? 60 trillion, right? No, 60 billion. There we go. I scale it to a million. I've got 60, so it'd be 60 billion there, right? So I know that regardless, the true coefficient estimate should be 60,088, regardless of the units, right? So I'm going to use this thing just so I make sure if you were to like work along with me, you get the exact same numbers. So what you can do in Stata is actually generate random numbers. The problem is if we all generate random numbers, what do we all have? Different numbers, right? If I set the seed here, I can kind of, they're still random, but I'm going to get the same set of random numbers. So that way we're all working with kind of similar values if you wanted to rerun this code. So I'm going to set this seed. I'm then going to do this thing where I create a variable that I'm going to call my measurement error. So my measurement error is going to be off from -1 to 1 here, right? So I'm going to run that. So if I look at this variable, I've now got random numbers between 1 and -1, okay? I'm then going to create this new variable, which I call BMI measurement error. So this is going to be my BMI variable. I just added in what that measurement error is. So I know that my dependent variable BMI is now going to be a little bit off. On average, what is my measurement error here? I'm randomly generating numbers from -1 to 1. The average will always be. So I've got my classical measurement error, right? So I'm just going to create this new BMI variable that has some measurement error in it, okay? So what I can now do is say, okay, I know what the true coefficient should be. What should my new coefficient be? Right? Well, I chose this random from a uniform distribution. So here, what is the estimate that we're going to see when I run this regression with my BMI measurement error variable? It should include that true estimate, which was like what? About 60,000, right? Multiplied by, well, what's the variance of my BMI variable? So we could actually go back and look at this and say, oh, okay, well, sum that original BMI variable. I'm just going to jot this down before we switch over. So it looks like my standard deviation is what? 2.19. So my variance would be 2.19 squared. I'm going to write this down before we switch over. And then what do I also need? I need the variance of my measurement error. So there, what, 0.58. So 0.58 was my standard deviation. How do I get my variance? I would just square that. Okay. So I can use that sum command to figure out what was the variance of this measurement error variable I created, and what was the variance of my original X variable BMI. So what estimate should I see if I plug this in? Well, I've got the variance of my measurement error, the variance of my BMI, the actual coefficient, because I had the original data, the estimate I should see should be this, right? So if I plug that into my calculator, what do I get? So I'm going to try to do this here real quick. So it's what? And it wasn't actually 60,000. What was it? It was a little bit different. 60,088. All right. So just to kind of show you. So I got 60,088 was the original coefficient times what? 2.19 squared divided by 2.19 squared plus 0.58 squared. So I should see about 50, I'm rounding too, so it's going to be a little bit off, but about what? 56,000. So if I go here and I now run my regression with that variable that has the measurement error, what I should see, okay, it's a little bit off, right? Because of my rounding, and also we're dealing with large numbers, so that rounding makes a lot more. All right, I'm getting kind of around that value, right? Now, obviously here, like I said, it's going to be a little bit off because I'm rounding everything to the second decimal. If I keep things out to further decimals, I'll end up finding out that my estimate I should see was exactly equal to this value, okay? Does that make sense here? Like I said, I know this is a little off from what we just computed, but you have to, you know, kind of imagine when I'm saying even 0.58, where was it at? Yeah, 0.58. I really should be keeping this all the way out to this decimal and then squaring it. I should be keeping this all the way out to that decimal. And so when we're dealing with these larger values, it's just going to cause a little bit more discrepancy when we're rounding there. But that's basically, right? We see, one thing we can definitely see is when I include that measurement error, what happened to my estimate? It was lower, right? I get this attenuation bias, okay? Now, if I ask you a question like this on your next problem set, obviously like the rounding is causing some issues. As long as you kind of report to me what those values you're using, like that'll be graded accordingly, right? So all you're looking for are the variance there of your variable, the variance of that measurement error, and then, you know what the actual coefficient. So actually, I'll set this up slightly differently. Let's say I run this regression and I see this is my coefficient estimate. And I know that the measurement error, I think, has a variance of whatever we said, 0.58 squared. And another researcher tells me, yeah, I actually had some BMI and some self-reported BMI data. And I can tell you that here's the measurement error and here's the variance on what the actual BMI measures should be. Well, then from my data set, even though I only have self-reported BMI, if I know the variance of my measurement error, I know the variance of the actual BMI values from this other researcher, I now instead can see my coefficient estimate of about 54,000. Let's say I didn't know this. Well, now I can actually figure out what the actual effect should be from my data set by taking this data from the other researcher, and now it's just a little bit of algebra, right? So I can work in either direction. So more often than not in practice, we're going to have the data that probably has measurement error in it and have to rely on someone else that has a different data set to kind of give us an idea about what the variance of the actual BMI values look like and what the actual kind of variance of that measurement error looks like. Okay. To kind of give a little more context, if I'm interested in like how BMI is impacting consumer spending habits, there's likely a data set that exists with self-reported BMI and kind of spending habits, but that probably doesn't have like actual recorded BMI. But who might have that? Someone over in the science, like the physiology department, probably has a study where they actually recorded with however they, very precise measuring tools, actual BMI and then self-reported BMI to get an idea of what that actual kind of measurement error looks like. So we might have to rely on other people to kind of piece together things sometimes. Okay. Does that make sense what I'm getting at there? Okay. Yeah.
Work the same for nonlinear models as linear.
So this should apply to whatever models we're thinking about. As long as it's classical measurement error, we're just talking about, so it could be the coefficient on a log-log term, could be the coefficient on a log-linear term, could be the coefficient. It would be a little bit different if we're looking at the coefficient of a squared term. Why? Because it's not actually beta 1. What's the coefficient of the square? It would be a separate coefficient, and we still have the underlying. So it would apply to our log linear models. It would be a little bit more complicated math if we were looking at the marginal, like looking at the total effect of a change in X from a squared model. Is that what you're asking? Yep. I won't push you guys that far. Yep. But yeah, if we did a log model, we would do the exact same thing. Yep. All right. Any other questions before we keep moving here? So to kind of make this point, let's say I then, because I can do this, create a new random variable, which is a really large measurement error. So instead of from -1 to 1, it's -10 to 10. Well, the expected value of my error is still, on average, 0, right? It doesn't depend on X, it's just random. So if I create this new measurement error, and then this new BMI, which is the original BMI plus this large measurement error, right? I'm just going to create those two variables. I then run this regression with the BMI that has this large measurement error. What should happen, right? Well, here, you can kind of think about, here was our coefficient estimate. And just to write it out in general terms, this was the variance of the actual BMI values, variance of the actual BMI values, variance of our measurement error. So if I just created a new variable in which I had even larger measurement error, what should be true about the coefficient estimate I see if I use the variable with an even larger measurement error in it? Well, if this goes up, my denominator is larger. If the denominator is larger, what happens to this fraction? It's going down. So I'm getting an even larger attenuation bias. So if I now run this regression with this new BMI that includes this huge measurement error, what should I see? Something much, much lower than what we had, about 54,000. It's going to be even lower than that. In fact, we actually run this. Not only is it much lower, it's much lower, right? As I start to increase that measurement error, I'm just pushing that estimate closer and closer to 0. So this is a good instance where before, if I looked at my non-measurement error data, well, highly statistically significant, and the value is 60,000. If I got a little bit of measurement error, okay, it caused some attenuation bias. My estimate's a little bit lower, but I could still say it's significantly different from 0, right? At any of our conventional levels. Notice if the measurement error gets too high, it pushes our estimate even lower. And what's going to happen now? Well, now we have a test statistic with the p-value. Can I say this is statistically significant or different from 0? I can, but only at the 10% level. I can't say that at the kind of 5 and 1 or the 95, 99% confidence levels. Right? So if you have large enough measurement error, yeah, it's going to cause an attenuation bias, but it can also then cause you to think that there's no statistically significant effect. Any questions on that idea? And if you wanted to, just because, well, where are we at for the sake of time? I think I'll save this for next class. Just to kind of prove to you. Okay. So I just did the exact same thing, but I threw 2s on everything, so I don't have to like drop variables. Let's say instead of 10 and -10, it's 1,000, -1,000 to 1,000. Right? So if I run this, if I truly have a attenuation bias, what's the lowest possible estimate I should see? It's getting closer and closer to 0. So even with a really large measurement error, you'll notice here, oh, well, how did I end up with I actually didn't get a coefficient of 0? Well, I am getting a coefficient of 0. If I look at the p-value here, can I say that this is statistically anything different? No. Right? So as you start to get closer and closer to 0, theoretically, technically, you could end up with a coefficient that doesn't look like it's 0. Right? If you ever were to find a negative coefficient, you are always going to have that you can't say that it's anything different than 0. Right? So if you have a large enough measurement error, yes, technically from the results you see, it could push it kind of past that 0 point. But if it ever does that, it's never going to push it far enough to where you then have statistical significance where you could say that's different from 0. Right? You're just going to end up with estimates that are like bouncing around 0. Right? So you could even, you know, if I wanted to do this, make it even larger, like, well, I don't believe you. Like maybe it pushes it far enough to where we can actually say it's statistically significant. So here I added some more zeros. Well, now it's positive, even though it's statistically significant. We're just getting closer to zero, right? It's just because every single time we're kind of getting a different random set of numbers, it's going to be bouncing around really close to zero. We're either going to say that, you know, it's statistically insignificant, or sorry, statistically not significant from zero, or we're going to end up saying finding estimates that are really, really close to zero, right? 9 is very close to zero. When we're looking at it relative to the actual effect, what was the actual effect? 60,000, right? Okay. All right. So that's measurement error in our dependent variable. And that was kind of classical. So the next thing we could look at is non-classical measurement error. So we'll talk, I think, a little bit more about this next class. Just, you know, I don't know if we'll have time to kind of flip it or kind of go through it really in detail in the next 10 minutes. But here I've got examples. We can see it's going to change that estimate quite a bit. Could flip the sign. It doesn't have to be attenuation bias. Could make it higher, could make it lower. So we'll look at non-classical measurement error instead in the next class. We'll then switch to thinking about, all right, we had measurement error in our independent variable, the right-hand side. What if we have measurement error in our dependent variable, right? And we'll end up seeing that doesn't matter as much, okay? So it should kind of end us kind of here for today. Like I said, I think that we should be able to go through this stuff relatively quickly next class. There's some of this stuff that's just kind of a fun example that we can kind of talk through of a little bit more work to do in kind of Stata. And then I should have some extra time where I'll probably pull open either the actual, I will pull open the actual problem set, and we'll kind of think through maybe revisiting some of that interaction term stuff. Okay. All right. Any questions from me before we keep moving here? Should be it for today. So also what I didn't have today, which might also be likely I have one on Thursday, no in-class quiz today. So you guys are kind of free to go. I will post an announcement up on Canvas about I'm likely to change my office hours tomorrow. I don't think I'll be, did I say this at the beginning of class? No, I talked to you, that's why. So I likely won't be in my office hours tomorrow. I'm waiting on some emails. I might already have them waiting for me after class. I'm probably gonna have to move those to Friday. So Friday afternoon is primarily kind of what I'm thinking. I'll put up exactly when those will be on Canvas later today after I get those emails, and then make sure, you know, whether or not I'll be there. Even if I have to move them, I should still be available virtually during kind of the usual office hours tomorrow. So if you want to meet, kind of send me an email and I can send you a link to meet tomorrow virtually. Okay. Other than that, I will see you guys on Thursday.